I will begin with a word of prayer. Dear Heavenly Father, we thank you for this day. I thank you again for these students. Just ask you to bless our work today, Lord. In your name I pray. Amen. So I'll try to pick up more or less where we got to in Gamelin to start with here. So we had discussed the fundamental group and how to calculate it using, if we had a covering map, right? And basically there's this one-to-one correspondence between the inverse image, like the fibers of the covering map, and the homotopic classes of loops. And so we went into that in considerable detail in the previous class, but I wanted to try to pick up on the end of the section where he says, now we return to the prototypical covering map. So we go back to where we started. P covering map from R, and this is again to be the pointed space notation, R paired with 0 to the circle with base point 1. So this is the, this is not Cartesian product of spaces or something. We're talking about a topological space and a point. The pointed space idea, all right? From pointed space R with point 0, pointed space S1 with point 1, all right? He says since P inverse of 1 coincides with the integers, right, as a subset of the reals, he says the element of the fundamental group, he says this means that pi 1 fundamental group of S1 based at 1 is in one-to-one correspondence with the integers. All right. He says he wants to now show that this correspondence is in fact a group isomorphism. And he says for this we will consider in detail the procedure by which a loop in S1 determines an integer. So let me draw a picture. Here's my S1, right? And oops. Anyway, so this was the our picture for that before, remember? And he says let gamma be a loop in S1 based at 1, which is, I mean, I understand, it's hard to come up with problems which are computationally manageable for this level of course and the amount of time you have to spend on the example, but it is kind of disappointing what this means. I mean, what is a loop in S1 based at 1? Like if this is 1, right? Then it's just this, but not necessarily that, right? It could be but anyway, it begins and ends at 1. All right? So that's a loop based at 1. Now, he says, consider the lift gamma of the lift of gamma is h from 0, 1 to r, right? So gamma, more complete, to finish my picture over here, of course, there's an unpictured domain of gamma at the moment, right? There's the domain of gamma, which I haven't even pictured. And that terminology lift we can see sort of more directly. Here's my interval from 0 to 1, right? So gamma is like this, yeah? Technically, it's the map from 0, 1 that loops around from 1 to 1. This one, of course, is a subset. We're viewing S1 here as a subset of the complex plane by default, right? That's our model for the circle, the unit circle, in fact. And the lift H, if I had to picture it in this picture, is a mapping from 0, 1 up to R, where I'm envisioning R as the helix again, like we did, right? So this is H, though, right? And how is that H related to gamma? Like, what's the rule? How does it work? Such that what? Such that E to the 2 pi I H of S, right, equals to gamma of S. And H of 0 is equal to 0. So up here somewhere on this helix is 0, right? Somewhere up there is 0. And H of 0 is, so like 0 maps to 0. And then what happens is what does H do? It's a path up on the helix, right? It's a path in the covering space of the circle. And he says the terminal point, H of 1, is an integer. All right? And that is what we let's see here. So why is H unique? Before I go on, can you remember? So we have supplied the point which starts the lift, right? And so then the path lifting lemma says there's a unique lift, given this upper point here that we're starting at. And then what else is the condition? How's it go? P of, I can't remember. Is it P of H? P of H of S is equal to gamma of S? That's the condition, right? But the P map was what? Remember what it was? It was P, P of e to the, how's it go? Can't remember. Pt equals to e to the 2 pi it, is that right? I want to say that was the map, wasn't it? Yeah. So this condition is that, right, for this particular definition. And so H is uniquely given by the path lifting lemma, right? And he says that this H of 1 is what defines the index of gamma, is by definition this. So, and also, I think we proved last time that for if we were to look at any other gamma which was homotopic, right? If gamma 1 was homotopic to gamma 2, then the index of gamma 1 would be equal to the index of gamma 2 as I've currently defined index. Which means we could just as well define index on homotopy classes, and that's probably what I should do, right? So this is a transitional definition. The real definition, I mean, the index, well, actually, I should back off for a second here. Well, no, he does define index to be on gamma. But let's say, fine, here's the map, phi of the homotopic class of gamma equal to the index of gamma. This makes phi a mapping from the fundamental group of the circle, right, based at 1 to integers. And the claim is that this mapping is in fact an isomorphism. All right? And he says to prove it's an isomorphism, what do we need to show? Right. The index. The index, yeah, the index. So you're essentially, to show this, it remains to show that the index of the well, not the composition really, but the join, you know, that path. I mean, basically, this loop followed by that loop is equal to the index of the first loop plus the index of the second loop. I really don't want to go through the details of this. I mean, you can look at the details, but I'd like to argue more geometrically for this one, if you don't mind. What the index here is, right, is it's the winding number. It's the number of times the loop encircles the circle. How can we see that? Suppose that gamma goes once around the circle. Let's work through it. Yeah. Right. Let's suppose that we're looking at the specific loop that goes counterclockwise around the circle one time. Right. So if I can draw it starts here, goes counterclockwise all the way around just the once. So that specifically is gamma of t equals to what? Well, gamma of s, rather, is e to the 2 pi is. I mean, this is the parameterization of that circle. That is it. Okay? Then I look at that. I set that equal to e to the 2 pi I h of s. Right? What does that tell me about h of s? Right? That says that h of s is equal to s plus some integer k, where k is, well, like I said, where k is an integer. That's just by the 2 pi periodicity of the exponential function. If these are equal, like if you have e to the I theta equal to e to the I beta, what that means, because sine and cosine are building the imaginary exponential, that means that theta minus beta is equal to 2 pi, 2 pi j, let's say, for some integer j. But the thing is here, I've got this 2 pi already here. So it just ends up being that if I shift by an integer, I'm shifting by 2 pi in the multiplication thing that multiplies the I. So that's why I have just s plus k rather than the direct. Okay? So that I hope that shows you that h of s is completely governed by some integer. k. What is that k? What else are we told? We're told that, by definition, h of 0 is 0. So that fixes h of 0 is 0, right? I mean, 0 plus k. See, for this loop, the index is 0. K is equal to 0 in this case. Wait a minute. What have I done? Oh, man. What have I done? Son of a gun. That's not right. Oh, the index is h of 1. K is equal to... K is not the index. Don't let me talk you into that. That's crazy. Is h the is k the index? No. Look, it's right here. So I just showed that k is equal to 0 for this once times around map, right? So h of 1 is equal to s is equal to 1, right? Plus 0, which is equal to 1. As I was claiming, one loop around gives you k. Let's go through this same explicit thought process for other parameterizations of the circle. Suppose, as our second thought process, suppose that you wanted to loop around the circle counterclockwise m times. What would the parameterization of, let's say, gamma m be for the m times encircling, round and round and round and round m times? What's the parameterization of that? It is e to the 2 pi I ms. We just speed it up m-fold times. Then we're going to go around, as we cycle from 0 to 1, we're going to 2 pi m times 2 pi m angle, which goes m-fold times around the unit circle in the counterclockwise sense. Right? But what does this say? So tracking through the same calculation, if gamma sub m of s is e to the 2 pi ms, put that puts an m here, right? And what do we get? We get that h of s is what? ms, right? ms plus k. So again, still h of 0 is 0, right? So this silly k is always 0, no matter what kind of winding I'm talking about. The reason that k is always 0 is because we're assuming that h of 0 is 0. That makes that quote-unquote k be 0. But on the other hand, this h of 1 is more interesting. H of 1, now with our new fangled m-fold wrapped m, is m. So the index is m. Like I was claiming, it is really the winding number. How many times your loop goes round and round the circle. Should probably take that. I don't know. I have mixed feelings. Like I don't see an ID. Is it anyway? So the winding number is m. Now, what if it was clockwise? What's the difference? What would the parameterization be if it's clockwise? Then you just change m to minus m. That makes it go the other way around, and the same calculation goes through, except that you'll get the index as minus m. So then the proof of the isomorphism is geometrically clear, right? If you take one loop and you go m times around, and you take another loop and then you follow it by going n times around, right? Then that's the same as doing m times around plus n times around, right? I mean, the sum of the winding numbers is equal to the winding number of the joint of the two paths. It's just geometrically obvious that this is true. So, okay, so Who is calling me? Usually, sorry guys. Phooey. All right. Sorry, I'm distracted. Now, all right, so there you go. We have this, this is not only is it a correspondence, it's in fact an isomorphism, but it's also an isomorphism which has like a direct and a beautiful geometric interpretation, right? Okay, so let's look at some theorems, some whoa! Oh, not a good sign. I spent, $5 for this book. Maybe 10, right? That just adds character to it, doesn't it? Some applications of the index, then. Let's get us to the next section here. Theorem 6.1. It says, let F be a map from B2 to S1 with f of 1 equals to 1, all right? Then loop alpha given by alpha of S equal to f of e to the 2 pi is, all right? Has index 0. What is B2? Yeah, I think, but I think it's the disk in Gamelin. I think it's yeah. So B2 is what you might call D2 in some other books. It's I believe it's, well, let's use complex notation. It's Z in the complex plane such that the modulus of Z is less than or equal to 1. In contrast, S1 is the boundary of B2, and that would be Z such that the modulus of Z is equal to 1. So, like, the boundary of B2 I could picture in red is a circle, and what's going on here? And here's 1, right? So it's saying we're taking a function from here to S1 such that 1 is fixed, and we're using that function to define a loop, allegedly here. Alpha of S is f of e to the 2. Now, is that a loop? Is alpha a loop, first of all? Does that make sense? I mean, the domain is right for the setup. It goes from 0 to 1, right? What's alpha of 0? It's composition of continuous functions, so it's continuous. It's a loop, right? And so how on earth do you calculate its index? Well, here's what he does. He says define loop beta, all right, in B2 by beta of S equal to e to the 2 pi is. right? All right, I mean, that's kind of what we were just talking about a second ago. I mean, that's just the counterclockwise parameterization of the unit circle. I mean, it's a loop, sure enough, right? And how does alpha and beta relate? This is note. Alpha is equal to F composed with beta. Is that right? Yeah. This is just manifestly true. And then what does he say? He says, since B2 is convex, corollary 4.2 shows that alpha is homotopic with endpoint fixed to the constant loop in S1 at 1. Since B2 is convex, that implies that, well, let me write it in this way. Pi 1 of B2 is what? What's the fundamental group of a convex set? Yeah. What's that? It's 0, right? What does that mean? Right, so all loops based at 1 are homotopic. So that means that, alpha is homotopic to the constant. Now, what does beta have to do with anything? Why do you have to bring beta into the mix? What was that? What was the point of that? Well, alpha was not a loop in B2, was it? Alpha was a loop in S1. He's saying beta is a loop. I mean, it's kind of a point of, isn't alpha? Was alpha really? Well, alpha was a loop in S1. What? I'm sorry, guys. What's the purpose of beta here in this argument? Can you explain? Alpha is homotopic to beta in B2, you think? Why is, okay, so alpha, so both alpha and, we can either look at alpha, so you're saying is we can either look at alpha and beta as loops in the circle, or we could look at them as loops in B2. Looking at them as loops in B2 is productive because B2 is... Why can't we always prove all loops around the circle are homotopic to... Right, something missing in our logic here, because it seems like if you're just sloppy about that, why can't we prove that all loops on the circle are homotopic? I can always just say, oh, they're really a loop on the boundary of the disk, and therefore are homotopic to each other. Something's wrong with that idea, because we just seen that they're not homotopic. Is in B2 only. The homotopy between alpha and beta is in B2 only. Right. Right. So you're saying is the homotopy equivalence of two loops in B2 does not imply homotopy. Two loops being homotopic in B2 does not imply that they're homotopic in a subset of B2 necessarily. Okay. I mean, I understand. I mean, if I can find my way to seeing why alpha is homotopic to the constant map, then the fact that the index is 0 is immediate, right? The constant map doesn't go anywhere. How many times does the constant map loop around the circle? 0 times, right? So once we have that alpha is homotopic to the constant map, then the claim is true, that the index is 0, right? But why is alpha homotopic to the constant map at 1? Lift F to the covering space of F1, S1? Mm-hmm. What happens to the constant loop under F? So the constant I mean, that's true because it's at 1 and it's at 1, right? I mean,
it's because of corollary 4.2, which says that if we have two paths in B2.
corollary 4.2?
Yes.
Two paths in B2?
Yeah, so one of them is beta. That's why beta.
Oh, so alpha and beta?
I would just say beta and then whatever the constant loop is. So those are two paths in 4.2.
So is it both from 0, 1 into B2?
Yeah.
Okay.
And then corollary 4.2 says that if we have a map from a convex space, which would be B2, to some other space, so in this case, F is our map.
So S1, I guess.
Yeah. It says that F of beta is homotopic to F of the constant loop.
Okay. All right. I'm sorry. I just, if I that is in fact, of course, what he says in the proof. I'm just not reading it right. Yeah. Well, with that, I guess we're done. I guess then that begs the question: why is corollary 4.2 true? Right. But, all right. All right, so anyway, this is theorem 6.1. And he says, theorem 6.2, here it is, there is no map from B2 to S1 such that f of z equals to z for all z in S1. So you can't find a continuous map from the disk to the circle which fixes every point. Is that true? Doesn't seem right. Like, why can't you just make the edge go to the edge and make everything else go to 0? Because that's not continuous, right? So you have to. Huh. Okay. Here's the proof. He says if there was such a map, so suppose that there exists f from B2 to S1 such that f of z is equal to z for all z in S1, then what? Then S maps to e to the 2 pi is would have index 0. By theorem 6.1. Right. I mean, f of 1 is 1, right? Yeah. But does that have index 0? It does not. We just showed it has index 1, right? So that's a contradiction. I haven't named the map, but, yeah. Related, theorem 6.3, he says any map f going from B2 to B2 has a fixed point. Do you guys know what a fixed point is? Emily, do you know what that means?
That's when like the phi of x equals x.
Right, yeah. So here, f of x equals x for this map, right? That would be a fixed point. He draws a picture for the proof. Let's see if we can understand it. What do you say? So he draws this he says, suppose that f has no fixed point, right? It's again by contradiction, right? So suppose there does not exist x in B2 such that f of x equals to x, right? Suppose it has no fixed point. Then what? He says for each z in B2, and here's a picture. He says let g of z be the point of S1 at which the ray issuing from f of z, okay, so f of z is a different point. Because why? Because we're assuming no fixed point, right? So f of z determines a different point. And then he says define G to be the mapping that's obtained by connecting the dots and extending to the edge of the circle. So like G of Z is going to be the uniquely defined point over here like this. Does that make sense? I mean, I don't know what that gets us. What does it get us? Hopefully it gets us the contradiction somewhere or another. All right. Then what? He says then G is a continuous map from B2 to S1. Let's see, is that continuous? Let's think about that. Well, certainly the process of, thinking about taking Z and mapping to Z minus f of Z, that's continuous because we're just taking the difference of the identity map and a continuous function. That's a continuous formula. And then if you think about what's required to get G of Z, well, that's just what? I mean, can you give me the formula for G of Z? I mean, this is a plain old problem of geometry. Can you give me the formula for G of Z, given how we've defined it geometrically? G of Z, right, is equal to Z minus f of Z hat, I think. Oh, I'm assuming it's in the middle, huh? Oh, man. Aw. Oh, phooey. It's not just the unit vector in that direction, eh? Oh, phooey. Fine. Well, yeah?
Well, I think it's kind of going around a little bit, but once you find the line through Z and C,
Uh-huh.
I'm just going to proceed with the proof of continuity in the space, like for every epsilon, such that it's in.
Well, I think once we find the formula for G of Z, it will be nothing more than the sum quotient product of continuous functions, and therefore will be continuous.
Maybe you have to write Z into a X and Y.
Well, how about this? Here's the, we're looking for the intersection of the, the line. So basically L of t is equal to, I don't know, Z plus t times Z minus f of Z, right? This is the direction vector in that direction, and this puts Z at t equals to 0. We're just trying to find a t such that this is an element of S1, right? which means we're just looking for the t which solves modulus of this, right? Equal to 1. Did I do it wrong? You want me to start at f of z? It's bothering you that I didn't put f of z here? I mean, yeah. Yeah. Fine. Now we've started at f of z. At time 1, we're to z. So, I mean, all I got to do basically is take this equation, right? Horrible as it is, solve for t, and this g of z is, well, let's say that this is L of t naught, right? Or t star. This is L of t star. It's the time where this gets to the edge of the circle. And I know it only gets there once. So we're going to have to get real to get an exact formula. Okay, at this point I've become disinterested in the details, but my point is, if you suffered a little while here, or if you're more clever than we're being at the moment, you could easily see that G is continuous. It's going to require, I mean, to prove the continuity, you're going to need to know that Z is actually inside the circle. The fact that the length of Z is less than 1 from the origin is going to matter to the proof of continuity here. I think. I could be wrong about that. I mean, certainly if Z is outside the circle, it can hit the circle more than one time, so the T star is not uniquely defined, right? If the point starts outside the circle, line segment would go conceivably through. Anyway, it doesn't make even sense after that point, but anyway, this is a continuous function of Z. I have waved my hands enough now. Now you believe it. And what's that give us? The proof is left as an exercise. See, we were exercising just now. G. He says. But if Z is an element of S1, right, then G of Z is equal to Z. Yeah, so exactly. So then, I mean, in that case, we can actually solve for T star. T star would be what? 1, right? In that particular case. So anyway, clearly this map fixes the boundary. So what's that say? Oh, but it does it for what? And which point on the boundary? Every point, right? So this contradicts theorem 6.2, which says that there is no such map. So that contradicts. is kind of neat. If you have any continuous map from a disk to a disk, there has to be some point which is fixed. If you think about what that means for like map making, it's kind of interesting, right? What would that mean if you think about like two different maps and like changing one, I don't know. I'm trying to think of what that would mean for map making. Okay, anyway, so the next theorem is the Borsak-Ulam theorem. Let F be a map from the sphere from S2 to R2. Then there exists an antipodal points W and minus W in S2 such that, so a related theorem to this, which I'll just write down here, theorem 6.4, it says that if you have F is a mapping from S2 to R2, all right, then there exist W and minus W in S2 such that F of W equals to F of minus W. Now, the proof is a little bit involved, okay? But if you look at it, basically what's going on here is he looks at, essentially, I mean, just to sketch the proof, he defines G, a mapping from S2 to R2 by G of W equal to F of W minus F of minus W, right? So what is it, this mapping G, what do you need in order to show that theorem 6.4 is true? You need to show that the mapping G does what? It has a fixed point. Well, it has a 0, right? We need to show that this mapping is 0 somewhere. I was laughing. Sprano had his face pressed up against the window a second ago. He's gone now. Don't humor him. See here. Come on, stupid watch. Worthless. All right. And what he does is he connects the sphere to the disk with the natural like projection x, y. Well, it's not the projection, it's the lift of the disk up to the sphere, up to the upper hemisphere, x and y mapped to x and y. And to get the z, you take the square root of 1 minus x squared minus y squared, which gives you the point over, I mean, all I'm saying is there's a map that takes you from B2 down here up to the upper half of S2. You know, that map. He calls that H. And he points out that, well, anyway, I don't want to go through all the details here, but all of a sudden, he takes that map and he normalizes it. And so doing, he constructs a mapping from the disk to S1, which maps 1 to 1, and that gives us a loop which has index 0, and then he shows through this calculation that the loop also has odd index. Of course, it can't have index 0 and also have odd index, but it's rather like, what? But the theorem itself is enjoyable, right? I mean, this is an interesting thing to know. If you have a mapping from the sphere to the plane, there has to be a pair of antipodal points which map to the same value. Do you guys know any maps from the sphere to the plane? Yeah, stereographic. How does this work out for that stereographic projection map? I guess that, yeah, that pesky, huh. So, how's it go? Like that map, that point maps over to here, right? So removing that point from the sphere makes it not really a map on the sphere, does it? A sphere with a point removed is not the same as a sphere. Yeah. So we can't really say anything. Sorry, I mean, it's kind of disappointing. Here's an app. Yeah?
It doesn't have to be a bijection. So you could just make it some kind of, I don't know, simple weird map. Oh, it has to go to all parts. It may not be a retraction.
Well, I don't think it has to be a surjection.
Yeah, it doesn't have to be a surjection. So that's what I'm saying. I don't know one offhand, but I was thinking we needed to get some kind of surjection. I don't think it's possible.
Why don't you just rest the whole ball on top of the, like rest it at 0. And then the map is just defined by like, what do you want to do?
Maybe just like a shadow.
Yeah, why not? Put a light bulb right here, and then how would that map be defined? I can't picture. I'm sorry. Yeah. Oh, look, guys, I'm being way too. You get sucked into this world of defining every map by a picture, and you forget we got this thing called analytic geometry. We can write formulas, can we not? Is that not allowed? So, may I recommend that we define f of x, y, z equal to xy. This is a natural formula that defines a mapping from the two-sphere to the plane. But there are strings attached, are there not? X squared plus y squared plus z squared is 1. So notice that f of x, y, z is equal to f of x, y, minus z. Oh, phooey, that's not antipodal, is it? Dang it. I thought I had something.
So I don't know if we have to find the antipodal points.
Yeah, no, but I want to know, what are the antipodal points of this map? What's that? You're right, that's not the example. Oh, it's f of 0, 0, 1 equals to f of, it's the north and south poles, so to speak. Yeah, those are the antipodal points for this map. And the only ones, right? But this theorem is actually